Greetings. It is my pleasure to present you my current research project entitled Solving the Atomic Structure of Ultra-Thin Calcium Difluoride Layers on the Silicon 100 Surface. My name is Joshua Salazar, and this work was performed under the advice of Professor Henry Pinto at Tech University on Ecuador. At a glance, what stands out of this material it's a stripe-like structure that gets formed after a chemical vapor deposition process of calcium difluoride over bare silica. The current scientific literature points out its potential features. Let us remark its feasibility of high quality production via the chemical vapor deposition process and due to the current maturity of silicon technologies. But let's also remark its interesting properties. The stripes are just 1 nanometer thick and insulating, and its bandgap is almost 3 times bigger than the bare silicon. Those factors make it remarkable for molecular electronics. For example, organic molecules can be easily manipulated over them and electronically decoupled from the interactions coming out from the silicon surface. However, its exact atomic structure remains unsolved, as the best STM measurements return these kind of images of the stripes formation. To tackle that, we constructed the material using DFT with the VASP software running on Kindle 1 supercomputer. We started from a primitive cell of bulk silicon. About the parameters used in the calculations, the cutoff energy and the number of key points were converged by computing the total energies over a range of values until a change of less than 1 millectron per atom was found. The values that did the job were 450 EVs for the cutoff and a number of key points equivalent to 9 times 9 times 9, implying a great spacing of 0.035 inverse angstroms in reciprocal space. To compute the optimal volume, we calculated total energies by varying the lattice constant and fitted them to the Birch-Murnaghan equation of state. With the help of its second derivative times the optimal volume, we were able to get the bulk modulus of the silicon crystal. Our numbers differ in less than 4% versus the experimental data. Continuing, we constructed the surface slab using 8 layers of silicon and 15 angstroms of vacuum to neglect electronic interactions coming out from the periodic boundary conditions of the plane wave simulation. Then we used 2 unit cells and we allowed the surface reconstruction process to occur to get an accurate electronic structure. With the bare silicon ready, the next step was to construct the wetting layers of the material formation. We repeated 3 times the former silicon surface cells and employed this configuration as the chemical reaction mechanisms reported in the literature suggested. Let us note here that the calcium atom is physisorbed after the silicon etching. This fact motivated us to employ a DFT plus van der Waals approach using the functional OPTB86B with a van der Waals kernel. There are 2 kinds of patterns observed in the reported STM images. We called them in-phase and out-of-phase configurations, here in green and blue respectively. But what unit cell resembles the observed patterns of the wetting layer? Well, to recreate them, we proposed different combinations which resulted in a tree of possibilities we will be discussing in a minute. The last step was to propose an atomic configuration for the stripe-like structure, and again, after exploring our tree, the most promising result came out from resembling the 111 direction of the calcium difluoride crystal on top of the wetting layer. Now let us check some results. The density of states of the bulk silicon returned a semiconducting behavior, a bandgap of 0.55 electron volts. The surfaces, comparing the 1 times 1 versus 2 times 1 configurations, supported their argument of allowing the surface reconstruction process to occur, as the 1 times 1 displayed metallic behavior against the 2 times 1 with semiconducting nature. For the different possible wetting layer formations, and returning again to our tree of possibilities, we used the simulated STM images as criteria for comparing against the experiment. we can observe that it was not just a matter of inverting the order to get an adequate pattern. For example, in here we can see that this one does not get close to the experimental data, even being in the same voltage configuration of the STM. Neither did this option. So after a lot of trials, the best configurations for the in-phase structure was this one. And let us see it in more detail. For negative voltages probing the occupied electronic states, we can observe that the patterns are similar to the experimental wetting layers. We proceeded to also compute the simulated STM line scan at constant current mode to prove the surface topography along this broken line. And our line scan simulation, here in blue, got closer to the experimental data rather than the reported ones in the literature that were not using van der Waals. For positive voltages probing unoccupied states, we also recovered similar patterns and got a qualitatively better shape of the topography than the previously reported results of this material. By computing the density of states of the wetting layer surface slab, we can observe that the downmost silicon of the first layer makes a bigger contribution to the unoccupied states of the material. Now, about the out-of-phase configuration of the wetting layer, this atomic setup returned the best qualitative results. Here in green we can observe the negative voltages of STM, and in blue the positive voltages. Now, about the last stage of the CVD on the stripe structure, we computed the STM images at minus 2.5 volts of it, and also its density of states. However, it displayed a metallic behavior with almost no bandgap, and the computed STM image did not resemble the pattern observed in the experiment. From the partial density of states, we can observe that the gap is closed by its silicon contributions to the unoccupied states. So we considered further silicon etching during the CVD process, and we were able to get a band gap and also a pattern that closely resembles the experimentally observed patterns. It's important to note that DFT is underestimating the bandgap value as it is common on this kind of calculations, but the trend is kept. The ratio between the bandgap of the bare silicon versus the stripe experimentally is around 3, and in our case it's around 4. Therefore, our combined results help us to support our argument that we effectively solved the atomic structure of the ultra-thin calcium difluoride layers on top of the silicon 100 surface. The work in progress right now is to apply DFT plus U corrections and looking for the Hubbard parameter to improve the value of the bandgap. So the U values from each separate material have to be accurately found to define a correct simulation for the entire interface. A preliminary result is that the U value found for silicon was around 6 electron volts. The final step is going to be to publish a paper containing our theoretical study, which includes our improved results versus previously reported data. Thank you very much.